A mysterious object zipped through our solar system at incredible speeds in 2017, catching astronomers completely off guard and igniting one of the most fascinating debates in modern astrophysics. Dubbed Oumuamua, a Hawaiian word meaning something akin to a scout or messenger from afar, it holds the remarkable distinction of being the first interstellar object ever detected passing through our solar system. But by the time scientists realized something extraordinary was happening in the neighborhood, Oumuamua was already on its way out, receding into the darkness at a pace that made any follow-up observation a race against time. With only a limited window of data collected before it vanished from our instruments, we are not actually certain what it truly is, or which distant star system it originally called home. But simply being interstellar is not what sets Oumuamua apart from anything else we have ever observed. That honor belongs to what we actually watched Oumuamua do during its brief passage through our cosmic backyard. An event so strange, so apparently in defiance of the laws of physics as we understand them, that some scientists have turned to the explanation of alien technology as the only viable means to explain it. What is Oumuamua? What did it do that was so startling? And are there more objects out there like it, silently threading their way through our solar system even now? There are a great many predictions circulating in the science community about how many extrasolar objects pass through our solar system over any given period. Some researchers think we are regularly visited, with estimates as high as 10,000 such objects passing within the orbit of Neptune every single day. That figure sounds almost unbelievably large, so it is worth taking the time to understand why scientists arrive at a number so seemingly astronomical. The answer requires us to think carefully about the true scale of our solar system and the churning, dynamic nature of the galaxy we inhabit. The first thing to appreciate is that our solar system extends far, far beyond the familiar orbit of Neptune. Neptune is often treated as a kind of boundary marker in popular imagination, but in reality, the sun's gravitational influence reaches out much further. Beyond Neptune lies the Kuiper Belt, a broad disk of icy bodies and rocky debris left over from the formation of the solar system. And beyond even that, stretching outward to distances almost incomprehensibly vast, lies the Oort cloud. This enormous, roughly spherical shell surrounding the solar system is thought to contain potentially trillions of comets, all gravitationally bound to our sun at extraordinary distances. When we look up and see a long-period comet arcing gracefully around the sun, there is a reasonable chance it has made the journey all the way in from this remote reservoir, following an orbit so elongated it may take tens of thousands or even hundreds of thousands of years to complete a single loop. Some of the comets we observe making these long journeys toward the inner solar system would never have left the Oort cloud at all were it not for the gravitational influence of massive third bodies nudging and perturbing their orbits. These gravitational interlopers are often other stars, and this brings us to a crucial point that is easy to overlook. Our solar system is not stationary. We do not sit in one fixed place in the galaxy, as our everyday experience might suggest. Instead, we are constantly in motion, sweeping through the Milky Way on a vast orbital path around the galactic center. As we travel, we periodically pass within the gravitational sphere of influence of other stars, even ones that appear distant by everyday standards. Encounters at ranges of just a couple of light years can be sufficient to gravitationally perturb a comet sitting at the edges of the Oort cloud, sending it plunging down toward the inner solar system on a new trajectory. But that same gravitational nudge can also work in the opposite direction. Rather than sending a comet inward toward the sun, a passing star's gravity can pull a comet entirely free of the sun's grasp, ejecting it into interstellar space. That liberated comet then becomes a wanderer, drifting through the galaxy without any parent star to orbit. When you multiply this process across hundreds of billions of stars doing the same thing throughout the history of the galaxy, you begin to understand why astronomers believe the interstellar medium may be densely populated with hundreds of trillions of such nomadic objects. Our solar system is not unique in possessing an Oort cloud-like reservoir. It is reasonable to expect that most stellar systems form similarly extensive clouds of icy debris during their early evolution, and that over billions of years, stars have been exchanging these objects with one another through gravitational theft and ejection on a colossal scale. Interestingly, while comets are constantly being lost from our system and gained from elsewhere, what we have observed of Oort cloud objects so far suggests that the majority of comets in our own cloud did indeed originate with our sun. Their compositions tend to be broadly similar to one another, consistent with having formed from the same primordial disk of material that gave birth to our planets. This tells us something important. While interstellar visitors do pass through, they are generally distinguishable from our homegrown population, at least in principle. As the solar system moves through the galaxy, it inevitably crosses the paths of interstellar objects that have been torn away from their original home systems by exactly the kinds of gravitational encounters described above. These visitors tend to approach from the general direction of the constellation Lyra, specifically from Vega, simply because that is the direction our solar system is presently heading as it travels through the galaxy. Think of it like walking through rain. The drops appear to fall mostly from ahead of you, even if they are actually falling straight down. While the sun does gravitationally capture some of these passing objects, most are traveling far too fast relative to us for a capture to occur. Instead, they hurtle through the solar system on curved paths, their direction of travel altered somewhat by the sun's gravity before they continue on their way into interstellar space, never to return. Oumuamua is one such object. It was first detected in our solar system on the 19th of October 2017, spotted by the Pan-STARRS telescope at the Haleakala Observatory on the island of Maui in Hawaii. Initially, when astronomers first picked up the faint moving point of light, it was assumed to be a comet, a reasonable default assumption given its apparent origin outside the solar system, and it was assigned the preliminary designation C/2017 U1. However, upon closer investigation, something was missing. A comet approaching the warmth of the inner solar system should develop a coma, the fuzzy halo of gas and dust that sublimes off the comet's surface as ices are heated, and often a visible tail as well. No such coma could be detected around this object, no matter how carefully astronomers looked. That absence prompted a reclassification to asteroid status, and Oumuamua was redesignated A/2017 U1, becoming the first object in history to receive such a reclassification from comet to asteroid. Once astronomers had gathered enough positional data to properly calculate Oumuamua's orbit, something else became immediately apparent and deeply striking. It was moving far too fast to be gravitationally bound to the sun. Every object that originates within our solar system, whether a planet, an asteroid, or a comet, travels at or below the local escape velocity relative to the sun at any given distance. An object moving faster than that escape velocity is simply not in orbit around the sun. It is passing through. We describe such a trajectory as hyperbolic, meaning the path curves as it passes the sun, but never closes into an ellipse. The object comes in, bends around the sun, and then continues outward and away, escaping the solar system entirely. Oumuamua's trajectory was unmistakably, unambiguously hyperbolic, and the implications were profound. This was not something born in our solar system. It had come from somewhere else entirely, from another star system around which it had presumably once formed, and it was simply passing through ours on a journey with no return. Because its velocity will see it leave the solar system altogether, it likely didn't come from the solar system to begin with. The object was thus given its Hawaiian name, Oumuamua, meaning scout, or first distant messenger. The International Astronomical Union had the unusual task of having to create an entirely new classification of object just for Oumuamua, something that speaks to how genuinely unprecedented this discovery was. They decided upon I for interstellar. So Oumuamua's designation now is 1I/2017 U1. As the first confirmed interstellar object we have ever detected passing through our solar system, scientists were understandably excited to study Oumuamua, eager to learn what characteristics it might have that made it similar or dissimilar to the asteroids and comets we find in our own cosmic neighborhood. Scientists quickly noticed that there was something strange about this object. It was small, perhaps between 100 and 1,000 meters long, and was believed to have a deeply unusual shape, perhaps resembling a cigar or a flat dish, depending on which model astronomers favored. Scientists inferred this shape because its brightness pulsated dramatically over its roughly 7-hour rotation period. When the object's longer axis was oriented toward us, we received significantly more reflected sunlight than when it was oriented edge-on, producing that rhythmic brightening and dimming. This variation in brightness was extreme, far more so than any asteroid or comet we had observed before. However, the same pattern of light could apply just as easily to a saucer-shaped object, meaning the exact geometry remained genuinely ambiguous. Adding to the strangeness, Oumuamua also appeared to be tumbling erratically, rather than rotating cleanly along a fixed axis, as most space rocks do, giving it an almost chaotic, end-over-end motion as it hurtled through our solar system. Oumuamua is unusual for more than just its shape. Because it appeared spectrally similar to an asteroid, it must have originated from the inner, rocky part of whatever star system gave birth to it. But that raised an immediate puzzle. How did it get ejected from its home system in the first place, and what kind of journey did it take to eventually reach us? Could it be the product of some ancient, cataclysmic collision of enormous proportions that flung rocky debris out into the interstellar void? Alternatively, maybe it really is a comet at heart, but one that had spent so long traveling through the cold emptiness of interstellar space, potentially for millions or even billions of years, that its surface had become thoroughly coated in a thick layer of radiation-processed dust. Such a crust could effectively seal away the volatile materials typically found on comets, meaning that even as Oumuamua swung close to our Sun, those ices were never exposed enough to behave the way we would normally expect. But while these puzzles about its origin and shape were deeply intriguing on their own, the thing that really set Oumuamua apart from anything we had seen before was its motion. Oumuamua passed its closest point to the Sun on September 9, 2017, traveling at a brain-melting 87 kilometers per second, fast enough to cover the distance between the Earth and the Moon in less than 5 seconds. But when it headed back out into the depths of space, it didn't slow down the way any ordinary object should. Scientists watching it detected an inexplicable burst of acceleration, one that was actively working against and counteracting the pull of the Sun's gravity rather than simply riding it. Rob Warwick, the researcher credited with the discovery, put it plainly when he said, "Its motion could not be explained using either a normal solar system asteroid or comet orbit." The rate of acceleration was relatively minor in absolute terms, only about 17 meters per second when it was nearest the Sun, and yet this deviation was precise and consistent enough to cause a genuine stir across the astronomical community. Oumuamua was simply not doing what the laws of physics said it should do, and that is not a sentence scientists use lightly. Over the next few months, during which scientists were able to observe it, Oumuamua continued deviating from the trajectory that gravity alone would predict. In physics, objects do not spontaneously accelerate. Something must push them. So scientists began the systematic work of trying to identify what force could possibly be pushing Oumuamua along. Several initial hypotheses were considered and quickly ruled out. Solar wind, the constant stream of charged particles that flows outward from the Sun, was one early candidate. It is a well-documented phenomenon that these particles can exert a small but real pressure on objects in space, nudging them ever so slightly. But the calculations didn't hold up. The force from solar wind was simply too weak to account for the observed acceleration, at least if Oumuamua had anything close to the density of a normal asteroid. Scientists then reached for another well-understood mechanism seen in our own solar system, outgassing, the process that drives cometary acceleration. As comets travel close to the Sun, the heat causes ice beneath their surface to warm and sublimate, transforming directly from solid to gas and venting explosively from the comet's body. This outpouring of gas and dust is what forms the comet's iconic luminous tail, but it also provides a genuine physical push, acting like a natural thruster on the sunward side that nudges the comet away from the source of the heat. It was a compelling explanation, and it was exactly the kind of non-gravitational acceleration that Oumuamua seemed to be experiencing. There was just one critical problem. Scientists could not detect any of the dust or gas that outgassing would inevitably produce. To be thorough and certain about this, the Spitzer Infrared Space Telescope devoted 30 full hours to attempting to pick up any kind of infrared signal from Oumuamua whatsoever, and came back with nothing. The object emitted no detectable infrared radiation at all. This was a striking result because typical comets produce highly visible comas and tails packed with dust and gas that Spitzer can spot with ease, as clearly seen in comparative images of known comets. Oumuamua showed none of that. Whatever was accelerating it, it was leaving no trace that any of our instruments could find. Adding further intrigue to the debate, readings from the Spitzer Space Telescope also indicated that Oumuamua was at least 10 times shinier than a typical comet, a striking anomaly that would fit remarkably well if the object were composed of something metallic rather than the dusty, carbon-rich material we normally associate with comets. That single detail alone was enough to keep astronomers up at night. So what was Oumuamua, really? To understand how the scientific community tried to answer that question, it helps to look closely at a fascinating clash between two theorists, each armed with a compelling but very different explanation. The first theory was by far the most headline-catching, the kind that makes mainstream news and provokes furious debate in faculty lounges and comment sections alike. Harvard professor Avi Loeb promoted across numerous papers the striking idea that Oumuamua could represent alien technology, not necessarily a crude vessel, but perhaps an artifact, a remnant, or a deliberately engineered object sent from somewhere else entirely. He argued in 2018 that solar radiation pressure, the gentle but persistent push that photons of sunlight exert on surfaces, could account for the anomalous acceleration observed in Oumuamua, but only under one very specific and extraordinary condition: that Oumuamua was far thinner than scientists had originally assumed, somewhere between 0.3 and 0.9 millimeters thin. To put that in perspective, that is roughly the thickness of a credit card, stretched across an object up to 1,000 meters long. Loeb argued that an object with those proportions was simply too extreme to have arisen through any natural, geological, or astronomical process we know of, and that the most logical conclusion, however uncomfortable, was that it had to be artificial. He envisioned it as a kind of light sail, a large, flat, reflective sheet deliberately engineered to catch solar winds and use that radiation pressure to accelerate across the vast distances between stars, much like a sailing ship uses the wind, only on an almost incomprehensibly grander scale. This theory was met with considerable resistance from other members of the academic community, many of whom felt that invoking extraterrestrial intelligence was a leap too far when natural explanations had not yet been fully exhausted. The most sustained and rigorous challenge came from Daryl Seligman, a postdoctoral researcher at Cornell University, who became the second major theorist in this debate. Seligman co-authored a paper in 2020 that offered a different path forward. He proposed that the reason no outgassing had been detected from Oumuamua was not because there was none, but because Oumuamua was emitting a gas that was simply invisible to the instruments pointed at it, specifically molecular hydrogen. Unlike the dramatic jets of water vapor and carbon dioxide that betray an ordinary comet's presence, hydrogen gas is extraordinarily difficult to detect at interstellar distances. The telescopes observing Oumuamua were not equipped or positioned to catch it. Seligman proposed that Oumuamua might be composed entirely or largely of hydrogen ice, a so-called hydrogen iceberg, slowly sublimating as it was warmed by the sun. That gradual phase transition from solid to gas would have produced a steady, invisible plume, and it was the pressure from that escaping gas that was nudging Oumuamua along and producing the mysterious non-gravitational acceleration. It was an elegant solution, natural, physics-based, and free of any need to invoke alien engineers. Loeb, however, was not persuaded. A few months later, he co-wrote a paper that challenged the hydrogen iceberg model at its very foundation, asking a deceptively simple but devastating question: where exactly could such an object have come from? Working through the mathematics carefully, he demonstrated that the ambient starlight permeating the interstellar medium, even in the depths of space far from any particular star, carries enough energy that a hydrogen iceberg would have sublimated long before it could complete the journey to our solar system. Even if such an iceberg had formed in the coldest, densest molecular clouds in the galaxy, which represent the most favorable environments imaginable for hydrogen ice to exist, the object would have melted away entirely during the millions of years of travel required to reach us. The numbers simply did not add up. Loeb remained convinced that a natural explanation was insufficient, and that something more exotic, something artificial, remained the most probable interpretation of the evidence. His refutation was sharp enough and well-reasoned enough to send Seligman back to the drawing board entirely, and the hydrogen iceberg hypothesis was quietly set aside. But Seligman did not abandon the broader idea that invisible hydrogen gas could be responsible for the push. He continued to turn the problem over in his mind, searching for a mechanism that could produce the same effect without requiring an object made entirely of hydrogen ice. The missing piece finally arrived in 2023 when Seligman met with Jennifer Bergner, an assistant professor at the University of California, who brought a crucial insight from laboratory chemistry into the conversation. Bergner pointed to a well-documented set of experiments in which water ice, held at extremely low temperatures and bombarded with ionizing radiation, was found to trap pockets of molecular hydrogen within its crystalline structure. The radiation essentially preloaded the ice with hydrogen gas, which remained locked inside until the ice was warmed, at which point the molecular structure rearranged itself and released the trapped gas in a quiet, sustained outflow. The implications for Oumuamua were immediate and exciting. Water ice is extraordinarily abundant throughout the cosmos, far more common than pure hydrogen ice, and ionizing radiation in the form of cosmic rays is equally ubiquitous in the interstellar medium. An icy object drifting through space for millions of years would naturally accumulate a reservoir of trapped hydrogen through precisely this process, requiring no exotic chemistry and no alien construction. Drawing on Bergner's experimental insight, the two researchers collaborated on a paper arguing that Oumuamua deserved an entirely new classification. It was not a conventional comet, which releases visible jets of dust and gas from its surface, like a small gassy volcano, as solar heat burns through its outer layers. Nor was it an inert asteroid, drifting passively under gravity alone. Instead, it belonged to a new category they called a dark comet, an object that possesses a coma and produces outgassing, but does so invisibly, releasing trapped hydrogen rather than the dusty, reflective plumes that make ordinary comets so obvious to telescopes. Their model accounted for the anomalous acceleration in a physically coherent way. It also explained the puzzling absence of dust, because a dark comet would not be blasting material off its surface in the violent fashion of a traditional comet, but rather quietly rearranging its internal structure and venting the invisible gas that had been locked inside it for perhaps millions of years. This was still not enough to bring Loeb on board. He co-authored 2 further papers in the following month, directly challenging Seligman's mathematics and maintaining that the data continued to support an artificial origin. The debate between the two camps remained vigorous and unresolved. Yet even as that argument played out in the literature, Seligman was already thinking beyond Oumuamua itself and asking a broader question. If Oumuamua was a dark comet, an object whose behavior had been misread for years simply because its outgassing was invisible, then the phenomenon was unlikely to be unique. Could there be other dark comets hiding in plain sight, already logged in astronomical databases, their strange behavior noted and puzzled over, but never properly explained? Seligman, Bergner, and a growing group of collaborators began methodically combing through existing observational data on objects already cataloged within our own solar system. These were not interstellar visitors, but homegrown bodies, and the question was whether any of them were accelerating in ways that gravity alone could not account for, and that lacked any visible sign of conventional outgassing. The answer, it turned out, was yes. When they finished their search, they had identified 6 objects that matched the criteria for dark comets, suggesting that this strange, silent category of celestial body may be considerably more common across the solar system than anyone had previously imagined. 6 objects had been identified showing non-gravitational, non-solar wind-based acceleration that couldn't be explained away by any known mechanism. These objects were small, some just as tiny as 3 meters across, which makes the mystery all the more striking when you consider how difficult they are to track at all. They looked like asteroids in most respects, displaying no remarkable surface features or obvious physical characteristics that would set them apart from the countless other rocks drifting through our cosmic neighborhood. They were near-Earth objects, all orbiting close enough that missions to them were not just theoretically possible, but extremely viable from an engineering and fuel standpoint. And yet, despite their seemingly mundane appearance, they were all exhibiting unmistakable signs of anomalous acceleration. To be clear, this acceleration was very minor, small enough that it had been overlooked in earlier observations, and only became apparent through careful, precise analysis. These objects are not zipping around the solar system from planet to planet like spaceships in a science fiction film. They are not interstellar objects blazing through on hyperbolic trajectories. But, just like Oumuamua, science cannot currently account for their motion. And that gap in our understanding becomes especially puzzling given that none of them show visible signs of outgassing, the process by which a comet expels gas and dust as it heats up, creating a kind of natural rocket thrust. Without that visible jetting of material, the standard explanations simply don't hold up. These objects have since been nicknamed dark comets, a term that captures both their comet-like behavior and their frustrating visual silence. And intriguingly, one of them is already scheduled to be visited before the end of the decade. The object, designated 1998 KY26, is due to be visited by Japan's Hayabusa 2 probe, a sophisticated asteroid sample return mission that launched in 2014 and successfully completed its primary mission 6 years later, returning material from the near-Earth asteroid Ryugu to Earth. Since then, the spacecraft has been given an extended mission, redirecting it toward other asteroids in the near-Earth Apollo group to squeeze every last drop of scientific value from this remarkable piece of hardware. 1998 KY26 is a fascinating target in its own right, quite apart from the acceleration mystery. It rotates exceptionally quickly, completing one full rotation every 10 minutes, which presents a unique set of challenges and opportunities for any spacecraft attempting to study it closely. Hayabusa 2 will aim to perform a flyby of this water-rich, tiny object, and the data gathered will be enormously valuable for planning future human missions deeper into the solar system, including eventual crewed missions to Mars, for which near-Earth water-bearing asteroids could serve as vital resource depots. Once the probe arrives and begins its observations, perhaps it will finally become clearer what is actually driving 1998 KY26's strange and persistent acceleration. The broader debate, of course, has not been settled. It's still not obvious who, among the various competing scientists, is correct about Oumuamua and about these dark comets more generally. But it is undeniably intriguing that more and more objects exhibiting this strange acceleration keep being detected. And it seems highly likely that a growing catalog of them will shed further light on Oumuamua's possible nature and origins. If these dark comets are found to accelerate through the invisible outgassing of molecular hydrogen, a colorless and essentially undetectable gas at interstellar distances, then Darryl Seligman and those who share his hypothesis will stand validated. It would mean that Oumuamua was simply an unusual but ultimately natural object, one whose behavior we lacked the tools to fully interpret at the time. But if a little hatch were somehow to open up on one of these rocks, and a small alien form were to peek out and wave at us before accelerating off out of the solar system, then we might regret not listening more closely to Avi Loeb. The former scenario is, of course, enormously more likely than the latter. There is no serious case for 1998 KY26 being an artificial light sail, because we have excellent imaging of this particular object, detailed enough to rule out the kind of flat, thin geometry that Loeb's hypothesis requires. But either way, whatever Hayabusa 2 finds when it arrives, it will be genuinely fascinating to study up close. Exploring these dark comets within our own solar system offers us a kind of indirect window into Oumuamua's nature, a way of testing hypotheses against objects we can actually reach and measure. But that still leaves a much larger question hanging in the background. What then of other interstellar objects passing through from beyond the solar system entirely? Have there been many others since Oumuamua first captured the world's attention? As it turns out, we have had other confirmed visitors from outside the solar system, though the next one on record is a considerably more conventional object. Being only the second confirmed interstellar object ever identified, it was given the designation 2I/Borisov, named after the amateur astronomer Gennady Borisov, who first spotted it in 2019. Zooming in on Borisov reveals an object that looked far more familiar than Oumuamua ever did. It had a large, billowing, comet-like coma and a distinct tail stretching behind it, together spanning a region almost 14 Earths across in apparent size. Despite this impressive display, it was never visible to the naked eye, as the closest it came to the Sun during its passage through the inner solar system was still beyond the orbit of Mars, keeping it too faint and too distant for unaided observation. Borisov was roughly comparable in size to Oumuamua, measuring about half a kilometer across. After reaching its closest point to the Sun and beginning the outward leg of its journey, it started to fall apart, fragmenting in a way that sounds dramatic but is actually reasonably normal behavior for a comet of this size passing a star at this kind of distance. Its composition, while somewhat uncommon in its precise details, did not reveal anything that would be considered truly alien or inexplicable. It looked, essentially, like a comet from another star system, built from the same broad categories of ice and rock that our own comets contain. Because it passed through the solar system at a much greater distance than Oumuamua, its trajectory was not dramatically reshaped by the Sun's gravity, which also meant there were fewer anomalies to puzzle over. So overall, apart from its prestigious classification as the second confirmed interstellar object in history, Borisov turned out to be a somewhat unremarkable visitor, a comet from elsewhere that behaved more or less exactly as comets are supposed to behave. Moving on from objects with the formal interstellar designation, there are other intriguing cases that blur the boundary between our solar system and the wider galaxy. The object cataloged as C/1980 was originally a native of our own solar system, locked into an enormous elliptical orbit with a period of around 7.1 million years. At its furthest point, its orbit carried it an incredible 1.17 light-years from the Sun, placing it deep in the outer reaches of the Oort cloud, and perilously close to the gravitational influence of neighboring star systems. However, during its last inward journey in 1980, it passed just a little too closely to Jupiter. The giant planet's immense gravitational field gave it a subtle but decisive boost, accelerating it just enough to reshape its orbit from a closed ellipse into an open hyperbola. From that point on, C/1980 was no longer truly bound to our Sun. It will continue drifting outward and, in a few million years, will quietly depart the solar system entirely, becoming an interstellar interloper in its own right, a native of our neighborhood turned traveler of the void. The reverse process has also been observed, and it is equally remarkable. There are cases where objects arriving from interstellar space have had their velocities slowed sufficiently by close encounters with Jupiter that they became gravitationally captured, effectively adopted into our solar system, and locked into orbits that will keep them here for the foreseeable future. Gravity, it turns out, is as capable of collecting wanderers as it is of flinging them away. Jupiter is mentioned specifically here because it has been determined that other planets simply aren't massive enough to accomplish this kind of gravitational intervention, and it has to be a third body beyond the Sun and the comet itself that does the slowing down or speeding up. Machholtz 1 and Hyakutake C/1996b2 are potentially such captured interstellar comets from another planetary system entirely. The giveaway for objects like these are their highly elliptical orbits, which trace paths far more extreme than anything we'd expect from a native solar system body, combined with their very unusual chemical compositions compared to the vast majority of other comets we've cataloged. This makes them particularly interesting and scientifically valuable targets for future missions, since the solar system might have done all the hard work for us, capturing these interstellar wanderers and placing them within arm's reach, rather than leaving them scattered across the galaxy. There's one more telltale sign that an object might have extrasolar origins, and that is if it is orbiting retrograde to pretty much everything else in the solar system. Nearly all the planets, moons, and smaller bodies in our solar system orbit and rotate in the same general direction, a legacy of the rotating disk of gas and dust from which they formed. An object moving against that flow stands out immediately as something that didn't form here. A prime example of an object like this is 514107 Kaepaoka-Awela. What makes this object especially interesting is that it is also an asteroid, which sets it apart from most other interstellar objects we would expect to encounter. The leading theory is that the volatile materials that would have once made it behave like a comet have already burned off over immense timescales, which would suggest it was captured very early in the solar system's past, billions of years ago when the young solar system was still a chaotic, crowded place. Its orbit is also unusual in another respect, in that it is locked in a one-to-one orbital resonance with Jupiter, meaning it completes one orbit around the Sun in the same time Jupiter does, a gravitational relationship that has kept it stable in its unusual path for a very long time. While objects like these are deeply fascinating and add important pieces to the puzzle, they don't settle the central question of Oumuamua's nature, and there is still a great deal we simply don't know. For example, where did it actually come from? We don't have a definitive answer, but what we do know is that it came from very, very far away, from somewhere out in the wider galaxy rather than from any familiar corner of our own cosmic neighborhood. To try to trace Oumuamua's home star system, astronomers painstakingly calculated its path backwards over millions of years, essentially running the clock in reverse to see where it might have originated. It seems to have come from the general direction of the star Vega in the constellation Lyra. Scientists identified 4 possible home star systems Oumuamua could have departed from, with some candidates located as far as 81 light-years away. But none of these candidates have yielded definitive answers about its true origin story, and the question remains open. And now, Oumuamua is over 6 billion kilometers away, moving at 26 kilometers per second toward the constellation Pegasus, placing it at roughly the same distance Voyager 1 had reached when it turned its camera back toward Earth and captured the famous pale blue dot image. The comparison is humbling because Voyager took decades to reach that distance, while Oumuamua crossed it in a fraction of that time. Even if Oumuamua turns out not to be a piece of alien technology or anything quite so dramatic, it holds enormous importance as the first confirmed interstellar object ever observed passing through our solar system.
It is a messenger from another part of the galaxy, and we barely had time to read the envelope before it was gone. It comes as no surprise then that scientists are eager to take a much closer look. We didn't even notice it until 40 days after it had already passed its closest point to the Sun, and by that time it was already 33 million kilometers from Earth and receding rapidly. Ground-based and space-based telescopes were pushed into overdrive in a frantic effort to gather as much data as possible before Oumuamua slipped beyond our reach entirely. But just 2 months later, by mid-December of 2017, it had already faded and accelerated to the point where even the largest ground-based telescopes on Earth could no longer study it meaningfully. The observing window was agonizingly short. Left with limited data and far more questions than answers, some researchers have come to believe that the only way to truly learn more about Oumuamua is to send a dedicated mission after it. However, catching up to something like Oumuamua presents a genuinely formidable challenge, and it breaks down into 3 main obstacles that any proposed mission would need to overcome. The first obstacle is gaining enough speed to catch up at all. Oumuamua is already over 6 billion kilometers away and careening through open space at 26 kilometers per second. No chemical rocket that exists today is remotely capable of reaching that kind of speed on its own, making a direct rendezvous essentially impossible without some creative engineering solutions. Once any probe is managed to catch up, the second challenge is decelerating enough to actually study the object in any meaningful way. A spacecraft that screams past Oumuamua at high relative velocity would collect almost nothing of scientific value. The physics of interstellar interception demand not just speed, but control. And thirdly, there is the sheer practical difficulty of locating and targeting such a tiny object across such an enormous expanse of space.
Remember, Oumuamua is at most around 1,000 meters long, a speck tumbling through the vastness of interstellar space with no beacon, no signal, and no guaranteed position fix waiting at the other end of a years-long journey. Despite these formidable barriers, they haven't stopped serious research groups from drawing up detailed plans to attempt exactly that. While accelerating to the speeds necessary to catch up with Oumuamua is deeply challenging using conventional propulsion alone, it can be achieved through the clever use of gravity assists from other planets, essentially borrowing momentum from massive bodies to fling a spacecraft to otherwise unreachable velocities. The most ambitious and detailed examples of this kind of thinking come from Project Lyra, an initiative launched by the Initiative for Interstellar Studies. Their researchers have worked out two distinct trajectories a probe could follow to pursue Oumuamua. The first trajectory requires three distinct changes in velocity spread across several phases of flight. First, the probe is accelerated out of Earth's orbit and sent on a course toward Jupiter. Once it arrives at Jupiter, the probe actually slows down enough to fall inward toward the Sun. Less energy is needed to do this from Jupiter's vicinity than from Earth's, because Jupiter's orbital velocity is less than half that of Earth's, making it easier to shed the speed needed to fall sunward. As the probe approaches the Sun, it reaches the highest velocity of its entire journey. At this critical moment, the rocket engines ignite to deliver the largest possible acceleration boost for the amount of fuel the probe carries. This is a technique known as a solar O-berth maneuver, which exploits a counterintuitive principle of orbital mechanics. A rocket burn performed at maximum speed, deep in a gravitational well, yields a far greater change in energy than the same burn performed elsewhere. By harnessing this solar O-berth maneuver, researchers predict their probe would shoot out of the solar system at over 70 kilometers per second, more than fast enough to close the gap with Oumuamua over time. However, there are still a couple of significant problems with this first plan. A close approach to the Sun of the kind required demands a sophisticated heat shield to protect the probe's instruments and electronics. And while the technology for such a shield does exist, as demonstrated by the Parker Solar Probe, the shield itself weighs around 72.5 kilograms, imposing a serious constraint on how much scientific payload could be carried. Additionally, the overall trajectory involved, from Earth to Jupiter, inward to the Sun, and back out in the right direction, is quite a long and complex route. There is a more direct way to accomplish the mission. And finally, this plan calls for maneuvers that have never actually been carried out in any real mission before, giving it a low technology readiness rating, meaning considerable development work would be needed before it could be attempted with confidence. There is, however, a second way to pursue Oumuamua, and it sidesteps several of these concerns. The second trajectory proposed by Project Lyra works as follows. Launch from Earth, swing around Venus and Earth to build up speed, conduct a deep space maneuver to reorient the probe onto the correct heading, swing by Earth once more for an additional gravity boost, and then use a final gravity assist from Jupiter to catapult the spacecraft out into interstellar space on a course toward Oumuamua. This second plan has several important advantages over the first. It doesn't require a heat shield at all, since the probe never approaches the Sun closely. It follows a substantially shorter and simpler overall trajectory. And because the probe ends up traveling at a somewhat slower final speed as it heads into interstellar space, it would actually be easier to decelerate on approach to Oumuamua, giving instruments more time to collect high-quality data and making the encounter far more scientifically productive. Project Lyra has identified at least two viable mission profiles using this approach, with potential launch dates falling between 2030 and 2033, and a projected arrival at Oumuamua sometime around 2048. It would be a long journey, but for the chance to finally understand what Oumuamua truly is, many scientists consider it more than worth the wait. One of Project Lyra's mission designers, Marshall Eubanks, feels that a mission to Oumuamua is not just desirable, but inevitable. After all, researchers are already crafting serious proposals for missions to planets orbiting other solar systems entirely. Destinations so remote, they make Oumuamua look practically neighborly. Even a century from now, Oumuamua will still be dramatically closer than those distant stellar targets. The case for going after it, at least on paper, is stronger than it might first appear. But the question lingers. Could there be a smarter, more efficient way to get the data we actually want, without committing to the extraordinary challenge of a dedicated chase mission? What if we could have anticipated Oumuamua months in advance, rather than scrambling to study it only after it had already swept past us and begun its long retreat into the dark? That missed opportunity haunts astronomers. Astrobiologist Karen Meach of the University of Hawaii, who led the scientific characterization of Oumuamua in the frantic weeks following its discovery, says we'll soon be in a far better position to do exactly that for other interstellar interlopers that might cross our paths. NASA estimates that an interstellar object similar in size and nature to Oumuamua actually passes through the inner solar system roughly once per year. The reason we so rarely detect them is straightforward and somewhat humbling. They are small, they are fast, and the night sky is vast. We simply haven't had the tools sensitive enough to catch them in time. Until now. The Vera C. Rubin Observatory, poised to become fully operational in late 2025, represents a genuine leap forward in our ability to survey the sky with both breadth and depth. Crucially, it would be capable of spotting incoming interstellar objects a full 3 months earlier than the telescope that first detected Oumuamua. 3 months may not sound like much in cosmic terms, but in practical terms, it is the difference between having time to observe, plan, and potentially even respond, versus watching an object vanish before we've even aimed a telescope at it properly. Beyond its raw detection power, the Rubin Observatory will get to work building what astronomers are calling the Legacy Survey of Space and Time, an ambitious, decade-long project that will produce a database of roughly 2 million images of the night sky. This extraordinary archive will be ideally suited for identifying subtle changes in the heavens, from the slow drift of asteroids to the trajectories of newly arrived comets threading their way through the solar system. A 2023 paper estimated that the LSST could realistically identify up to 70 Oumuamua-like objects per year, a staggering increase in our exposure to the interstellar population passing through our cosmic neighborhood. Another forward-looking initiative aimed at better understanding these mysterious visitors is the European Space Agency's Comet Interceptor mission, currently scheduled for launch in 2029. The concept behind Comet Interceptor is as elegant as it is audacious. Rather than chasing a known target, the spacecraft will be placed in a gravitational parking spot in space and simply wait, for up to 3 years if necessary, for a suitable comet or interstellar object to present itself. When the right candidate appears on a trajectory that makes an encounter feasible, the probe will spring into action, executing a precisely timed close-range flyby and using its suite of instruments to build a detailed three-dimensional map of the object's shape, composition, and surface features. It is, remarkably, the first space mission ever launched with a genuinely unknown target, a kind of cosmic ambush lying patiently in wait. There is something almost poetic about that approach, a spacecraft sitting in silence among the planets, watching the darkness for something unexpected to arrive. And yet, both of these strategies come with significant limitations. There is no way to predict how long Comet Interceptor would need to wait before a suitably intriguing object happens to swing by on an intercept-friendly trajectory. If another Oumuamua-like object doesn't oblige within the mission's operational window, it would represent a painful waste of time, engineering effort, scientific talent, and public funding. More fundamentally, neither of these approaches would tell us anything new about Oumuamua itself. That object is now so far away, accelerating outward beyond the orbit of the outer planets, that no telescope currently in operation or on the drawing board could capture meaningful new data about it. Whatever secrets it carries, whatever clues about its origin, its composition, or its nature, are being carried away from us at extraordinary speed. The answers, if they exist, are drifting toward the darkest reaches of interstellar space with every passing day. Waiting patiently for the next visitor to arrive means accepting that Oumuamua's particular story is, for us, already over. Weighing these alternatives carefully, perhaps launching an interstellar probe to chase down Oumuamua isn't quite as extravagant or outlandish an idea as it initially sounds. From a purely technical standpoint, it is viable. Nothing about such a mission is fundamentally impossible, given our current understanding of physics and the propulsion technologies already under serious development. Solar sails, gravitational assists from Jupiter or the Sun, and advanced light-based propulsion concepts developed under initiatives like Breakthrough Starshot all point toward a trajectory where catching a fast-moving interstellar object is genuinely achievable, even if extraordinarily difficult. The engineering challenges are immense, but not insurmountable. The laws of nature do not forbid it. The harder question is whether it is economically and practically viable. Space missions are enormously resource-intensive, demanding not just money but decades of human expertise, rare materials, institutional commitment, and political will sustained across administrations and budget cycles. A mission to Oumuamua would require all of these things in abundance, and it would demand them at a level well beyond almost any mission we have ever attempted. Perhaps, some would argue, it is wiser to accept the loss and trust that the universe is generous with its visitors. If Oumuamua happened once, it will happen again. Our solar system will eventually be greeted by its next interstellar guest, and with better telescopes and faster response capabilities, we may be in a far stronger position to study that future arrival properly. Ultimately, the debate distills down to a deeply human question. What is the price we are willing to pay to scratch the itch of curiosity? It is a question that doesn't have a clean answer written in a spreadsheet or an orbital mechanics simulation. The researchers at Project Lyra are grappling with it seriously, running the numbers and making the case as methodically as they can. What makes it so difficult is that the uncertainty runs all the way down. Multiple competing theories have been proposed to explain Oumuamua and its catalog of bizarre properties, its unusual shape, its non-gravitational acceleration, its strange brightness variations, its apparent lack of a cometary tail. But without additional data, we cannot distinguish between a dark comet driven by exotic outgassing, a fragment of some shattered alien world, a product of processes we don't yet understand, or something altogether more startling. It may ultimately turn out that none of the theories proposed so far come close to the truth. And that possibility, far from being discouraging, is precisely what makes science so endlessly alive. The universe has a reliable habit of being stranger than our best guesses, and every time we venture closer to something we don't understand, our models of reality get a little more honest, a little more refined. Perhaps one day we will encounter further objects arriving from interstellar space, objects that share enough of Oumuamua's characteristics to help us build a more coherent picture, or that differ from it in ways that prove equally instructive. The search itself, even for dark and silent objects moving under forces we cannot yet see or name, is something that fills the imagination with a kind of marvelous, restless curiosity. It is the same feeling that has driven exploration throughout human history, the nagging conviction that the next horizon holds something worth knowing. Only time will reveal whether the missions proposed to recover more data about Oumuamua, or its kind, will ultimately be judged worth the extraordinary investment they demand. But that is the terrible, captivating irony at the heart of it all. Unless we are willing to take the gamble, to commit the resources and accept the uncertainty, we will never know what we gave up by letting it go.